We're going to continue looking at functions. We are always very interested in the domain because the domain tells us what we're allowed to plug in. So, when we are asked to find the domain of the function, we look for two things. The things that cause problems and do something you're not allowed to do. The first one is look for division by 0, because as we know, you can never divide by 0. The second one is to look for the square root of a negative number. Okay? Because even though we do allow complex numbers, we're never going to allow them on a graph, because to graph complex numbers is really complicated and you actually need 4 dimensions. We just don't want to go there right now. There will actually be 2 more things we're going to look for in domain, but we're going to put those off until later in the semester. So I have 3 examples of functions written in function notation, and I'm going to find the domain of all 3. So I look at this one first, f of x equals 7x plus 4, and I say, do either of these 2 things ever happen? Well, there's no division, there's no square root. This means the domain is everything, which I'm going to write using something called interval notation from negative infinity to infinity. Includes everything. Now, this one, I say, is either of the 2 problems present, and yes, there is a square root, so there's a potential to take a square root of a negative number. So to avoid that, when I'm finding the domain, I need the part inside the square root to be always greater than or equal to 0, so that it is never negative. I then solve this for x, and it gives me the domain. So the domain of this function is that I'm only allowed to plug in numbers that are less than or equal to 2. Our last example we look at, and I say, are either of these 2 problems present? Yes. There's a division. So, in order to avoid the problem, I need the denominator to never be 0, which means I need x to never be negative 2. Okay. All right. We also want to look a little bit about graph behavior. I have an example of a graph here. If you noted, it is a function because it passes a horizontal line test. There's a couple interesting things about this graph. Okay. Obviously, we have the y-intercept here, okay, and we have x-intercepts at these 5 places. Now, in graphs, x-intercepts have another name. They're called zeros of the graph. Zeros because that's where the y-coordinate is 0. Okay. So in this case, my x-intercepts or zeros are at x equals negative 2, 3, 5, 8, and 9. Now, other interesting points about this graph. Okay. I like to know where the highest or lowest points of the graph are. Okay. Now, notice these 2 high points are not the highest point on the graph overall, because this part over here on the right is going to keep on getting bigger and bigger and bigger forever. And these 2 low points are not the lowest point on the graph overall. So we can't call them the maximum or the minimum of the graph. What we call them instead is a relative maximum. Because close by this little point, it is the highest point on the graph. So we have 2 relative maximums and 2 relative minimums on this particular graph. The last thing we want to look at is the increasing, decreasing behavior. So obviously the graph is going up until there, then down until there, up, down, and up. Okay. We want to be able to identify increasing and decreasing intervals. So let's break the graph up into when it is behaving in each manner. First of all, it's increasing all the way to the left, so from minus infinity all the way until that 3. So it's increasing from minus infinity to 3. And then it is decreasing from that 3 to 4. Oh, we made a little mistake. Notice we care about the x coordinates here, not the y coordinates. So it's increasing from minus infinity to 1, decreasing from 1 to 4. Then it starts increasing again from 4 to 6. We put a little U for union in between these. Then it starts decreasing again from 6 to about 8.5. And then it increases from 8.5 forever or to infinity.